Okay, we are on calculating the heat of a combustion reaction, and the first practice problem says you have a 3-gram chunk of coal, which is solid carbon, and it's burning to produce carbon dioxide gas, and this is happening in a copper bomb. The mass of the bomb is 2 kilograms, and the mass of the water in which the copper bomb is immersed is 2.778 kilograms. The initial temperature is 21 degrees Celsius. The final temperature is 29.3 degrees Celsius. They want you to calculate the heat of formation of carbon dioxide gas. We need to calculate quite a few things here. We need to calculate the heat of the copper bomb, the heat of the water that it's submerged in, and then add them together to get the total heat. So the heat of the copper bomb is MC delta T. The mass was 200 grams. I converted kilograms to grams. You multiply that by the specific heat capacity of copper, which is 0.387, and then multiply it by the temperature difference, final temperature minus initial, you're going to get 642 joules. Then calculate the heat of the water that the bomb is immersed in, because the heat is going to leave the copper bomb and go into the surrounding water. That's going to be MC delta T. Convert the kilograms of water to grams, multiply by the heat capacity of water, and then the temperature difference, which is T final minus T initial. 9640 joules was the heat produced. Okay, now to get the total, add these two together. So the heat of the copper bomb plus the heat of water is going to be 102.82 kilojoules. Now, the heat gained equals the heat lost by a reaction. The heat of the reaction is negative 102.82 kilojoules, because your temperature rose, that's why it's negative, and it's exothermic. Take this value, divide it by the mass of copper, the mass of carbon rather, which was 3 grams. I multiplied it by the molar mass of copper, which is 12.01 grams per mole. That leaves you with units of kilojoules per mole, so you get negative 411 kilojoules per mole, and that is the heat of formation of carbon dioxide gas. Okay, now, if we're looking at number 2 says you have toluene, and we're going to place it in a bomb calorimeter with excess oxygen. You're given 750 milligrams of toluene liquid. The heat capacity of the calorimeter is 22.53 kilojoules per degree Celsius. When the calorimeter was fired, the combustion of toluene caused the temperature to increase from 23.002 to 24.415 degrees Celsius. Calculate the enthalpy change for the reaction. Okay, let's calculate heat by using Q equals the heat capacity C times the change in temperature. So 22.53 was the heat capacity of the calorimeter. Your temperature change was 24.415 minus 23.002 degrees Celsius, and that gives you 31.8 kilojoules. So that's what you get when 750 milligrams of toluene reacts. Now, take the mass of your toluene, we're going to convert it to grams. Let's divide it by the molar mass of toluene, which is about 92 grams per mole, so we can convert this to moles. And then to get the enthalpy change of the reaction, you're going to take Q and divide it by moles, so we have units of kilojoules per mole. So 31.8 kilojoules divided by 0.00815 moles is going to give you 3910 kilojoules per mole of reaction. Okay. Last problem, problem number 3. A standard calibration reaction is used to determine the heat capacity of a bomb calorimeter. The temperature increases from 1.275 degrees C because of the input 14,580 joules of energy. What's the heat capacity of the calorimeter? Well, if you take Q equals the heat capacity times the change in temperature, we're going to substitute 14,580 joules for Q, and we're going to solve for C, and then your change in temperature was 1.275 degrees Celsius. Just divide both sides by 1.275, cancel that. You're going to end up with 11.4 kilojoules per degree C, and that's for A. For B, it says use the data in the table of heats of formation to calculate the enthalpy change of combustion of methane. Well, we need a balanced chemical equation for this. So when methane combusts, it combines with pure oxygen, and you always form carbon dioxide and water. And then to balance this, I'm going to put a 2 in front of O2 and a 2 in front of H2O. Now, the state of matter is important here because the state of matter influences which heat of formation I use for water. Is it water vapor? Is it water liquid? So make sure you know we're forming liquid water, okay? Okay, so the change in enthalpy, the enthalpy change for the combustion of methane is equal to the enthalpy of the product minus the enthalpy of the reactant. So if you look back at the table, you'll see that you have negative 393.5 for CO2, and then you have 2 times whatever water is, which is negative 285.8 for liquid water. So that's your product heat of your product enthalpy of formations, and then subtract your reactant. This is pure oxygen, so it has an enthalpy of formation of 0. So we only need to look up methane, which is negative 749, or 74.9 rather. Okay. So anyway, you're going to end up with negative 890.2 kilojoules per mole. We're going to go ahead and throw out C. C is not really necessary to take a look at.